Hello, I'm Risto Mikkolainen, and I'd like to talk to you about some work we've done at Cognizant about optimizing COVID-19 interventions using evolutionary AI. So this is the big picture. How do we make decisions in general, in life, in business, in organizations, and in science? Typically, these decisions are based on past experience in similar situations, but also there's some trial and error involved in trying to find better solutions than we have in the past. And with ESP, or evolutionary surrogate assisted prescription, we are trying to automate and formalize this process. The idea is to learn two different models. The first one is a prediction model that's looking at historical data about what decisions were made in what context and how well they worked out. And you can use historical data to train such a model using standard machine learning. The other model is a prescription model, whose job is to look at the current context and decide what the best action is in that context. Now, we don't generally know what the best action is, so a different learning technology needs to be used, evolutionary AI, where we are exploring and searching and finding good solutions and then evaluating the candidates using the predictive model. So the predictor is a surrogate for learning good prescription strategies. So ESP can be used and has been used in many different decision-making domains. For instance, we've designed web interfaces that convert the users to click or buy or sign up as well as possible. We used it in cyber agriculture to come up with recipes that allow us to grow plants as efficiently and as good plants as possible. And various game-playing domains where decisions need to be made in order to play a good game. And even in business and marketing, for instance, to decide how to allocate dollars to different marketing channels. All of these can be posed as similar decision-making domains where surrogate modeling can be used to discover good strategies. Now, COVID-19 provides another such challenge. The idea here is a little different from what we've seen in most COVID-19 work in the last year and a half. Much of the work focuses on prediction. That is, you look at the current time series of the history of cases and hospitalization and deaths, and possibly also the interventions have been done. And then you try to predict what will happen in the future. For instance, how many cases are you going to have in the next 3 months or 6 months? And that's fine, but we would like to go a step beyond that and actually come up with prescriptions. What should we do about it? What kind of restrictions should be set in the society so that we keep the pandemic in check? So this is new, not just what will happen, but what should we do about it? We're learning the prediction and the prescription at the same time together over time. And the idea is that this way we also adapt to the different stages of the pandemic and can keep one step ahead of it, if you will. There's a detailed paper about it, and IEEE transaction evolution computation on this approach. I'm just going to give you the highlights of how this approach works. So the first step is to build a predictor with the data that already exists up to that point. And here we were using the data set that Oxford University compiled using cases and the MPIs in different countries in the world from the beginning of the pandemic to the current date. Now, this data can be modeled using various methods, and standard compartmental models have been used quite well on it. They are based on assumptions on susceptible, infected, and recovered individuals, for instance. It's fine. It just requires setting some constants that we don't quite know, interaction parameters, in order to fit the data. Our approach is a little different. It is to use the data itself and learn from the data itself using machine learning. And the advantage is that it requires no assumptions. All the assumptions are hidden in the data. And if you model the data well, you are taking into account the interactions. You learn what those interactions are, and then in order to predict well. Obviously, this requires sufficient data, but it turns out that actually there is now. In this pandemic, there's quite a bit of data across different countries, different stages, different policies, so we can learn from them. And importantly, the models also change over time as the data changes, as the pandemic progresses. So we can build these predictors that adapt to the situation and take into account interactions that would be difficult to formalize explicitly in the standard epidemiological models. So that was the first step. The second step is then to evolve the prescriptor, the decision maker. using the predictor as a surrogate. And here is a general architecture. It's another neural network. It's looking at the same time sequences, but now it's its output. It's recommending what to do. Close to schools, close workplaces, cancel public events, and so on. There are a number of different dimensions like that. And notice that there are no gradients. We don't know what the right actions are. So that's why we need to use evolution and evaluate every candidate of the evolutionary population against the predictor, because they are maybe recommending policies that have never happened before. So we cannot ask the real world what would happen. We can implement them, but we can ask the predictor what it thinks might happen. So here we are evolving all the parameters of the network, the weights of the network, and then we are evaluating each candidate network against two different objectives. We would like to minimize the number of future cases, and at the same time, we would like to minimize the stringency of the MPS, have as little restrictions on life and economy as possible. So these are, of course, conflicting objectives, so we get a Pareto front. And this animation here shows you how that Pareto front progresses over evolutionary time. When we are searching for good policies, we start somewhere here in the middle with trade-offs of cost and cases, and over time we find more solutions that are better trade-offs. They are in a lower left part of the graph. And this Pareto front then allows you to select how strict do you want to be in your goal of reducing cost, for instance, or how many cases can you afford. So then you pick what trade-off is acceptable to you, and then we have in this population, we have a prescriptor that matches that trade-off. So we've developed an interactive demo of this system, and it's on that website, and I have it here. This is the starting point. You have a map of the world, and you can pick a country here that is of interest. For instance, we can go and pick India, where there has been a recent peak of cases. And we see here the historical data on how the number of cases has progressed, and also what it's currently predicted to be given a set of prescriptions. So here in this slider, we can select from that Pareto front. Currently, the most stringent prescriptions are selected. So that means keep the country under a lockdown. And if we do that, the cases will go down quite well. But it turns out there are many other choices here, and we don't have to be quite so restrictive. We can open up the economy quite a bit. Many of these lighter colors indicate that other dimensions of restrictions no longer really matter, as long as we keep the schools and workplaces under control, as well as some public events and public transformation and stay at home. The number of cases is predicted to be still quite low. But if you go a little too far, it turns out things will not look so good. There will be another peak if we open up most of the economy, even if we still have some focus on how the workplaces work, we would be headed for another devastating peak in India. That's what the prediction is. And it allows you to explore what kind of restrictions might be necessary to get out of the pandemic and stay out. We can look at some other places. We can go, for instance, the other part of the world, go to the United States, where we are in a different stage of the pandemic, hopefully. It's largely over, and we're doing quite well, even with that kind of a restriction of only mostly focusing on workplaces and not much else. The number of cases should go down and stay down in the future. But we are not out of the woods yet. If we, at this point, open the economy completely, the system predicts that there will be another serious peak. Things will get out of hand. So we do have to restrict and have some restrictions still for a while. And this current one here, the recommended kind of a minimal cost, still keeps the workplaces mostly closed. And that might be something that you may not want to do. And you might want to explore some other alternatives. So the interface here allows you to do it in this demo. We can open up workplaces, just have some recommendations left, and we can trade it off with something else. For instance, we can continue requiring facial coverings, masks. And it turns out that this combination works pretty much the same. The number of cases will stay down, but this might be preferable to a decision maker. Let's look at it a little bit more carefully by zooming in. There's a green line that overlaps a bit of the blue line, showing that the number of cases will stay down, even though we are only adding the masks on the and lifting the restrictions on workplaces. So in this manner, the demo allows you to explore different parts of the world at different stages of the pandemic, and also edit and try out alternatives and see what kind of restrictions might be possible and implementable. And this way discover something that might work. Okay, so what have we found? What have we learned? A number of things. Interestingly enough, the system discovered early on that there are surprising things that you can do, things that we did not anticipate. A lot of times it happens about 2 weeks, maybe 4 weeks in advance before it became kind of a public knowledge and public focus. So for instance, in May last year, 2020, the system mostly recommended closing schools and workplaces. This, of course, eventually happened, and it helped us bring the pandemic down. And the reason was also understood that this is something where people spend a lot of time indoors, and transmission is likely to happen in schools and workplaces. It also came up with kind of creative solutions. For instance, this alternation, that maybe we don't completely close everything, but we alternate opening and closing times. There's only limited amount of freedom that the system can be creative with, but this is something that also has been suggested, and alternating cohorts, for instance, have been proposed. Later on, after the summer, there was another peak starting, and the system was changing what it was focusing on. Schools were no longer the focus because there was quite a bit of mitigation that was done in schools, dividers, masks, other things. And gatherings and travel restrictions turned out to be important, and made a lot of recommendations on those. But then in the beginning of 2021, some of the things that already had gone down came back. Stay at home and focus on schools again. And indeed, later on, we started to understand that that schools, for instance, are still vectors for bringing in the disease to homes where people work remotely, as well as limited movement turned out to be important, and places like UK and Australia and others have gone to another lockdown because of the other variants. So this was also something that the system anticipated and saw before it was actually happening. Later on in the spring and March, it was actually predicting that India was going into a big surge, and there was really nothing we could do about it, even if we tried to lock it down, and that indeed happened. And most recently, it noticed that Russia is due for a surge, and this happened again several weeks before, and there was not a whole lot of warning in the data, but it was able to predict that, and that indeed did happen as well. And this is important. This means that the system can find things before they happen, and while there's hopefully still is something that we can do about it. So in that case, it's actually actionable knowledge that can be used to control the pandemic. Now we are in a phase where we're also looking at the data of the past year and a half or so, and we can go and analyze what kind of recommendations were made and what might have worked and did work. This means looking at counterfactuals and retrospectives, and we find a lot, of interesting things. Here are some of the early ones that, for instance, in the UK, if the lockdown had been instituted a little bit before, a couple of weeks earlier, it would not have been necessary to actually lock the country down. Lesser restrictions would have worked to keep the pandemic in check. And these are the kind of things that we try to find and lessons to learn for future pandemics, and maybe even this pandemic in some parts of the world. There are also some limitations that we found, for instance, that the system could not really predict Italy and the early surge in Italy very well. And the reason probably was that it was learning from the countries far east, where the culture is different, and these lockdowns work a little differently than they did in Italy. And these kinds of cultural differences may need to be input as well into the system in order to make accurate predictions in the future. Okay, so we also took this idea to the whole scientific community with the goal of bringing them together with different kinds of approaches and building predictors and prescriptors that could be then brought together to an even better system. So this was an X-Prize competition, pandemic response challenge. It ran from November to March 2020-2021. And there were some 100 teams that started. The field was winnowed down in using the phase 1, the prediction accuracy as a metric. And then in phase 2, they created prescriptors and actually recommended interventions. And in the end, there were 2 winners of the prize, a team from Valencia and a team from Slovenia, and 8 runner-ups. And many different approaches were used. Indeed, as we anticipated, it was possible to solve these problems in many different ways. And there were quite interesting insights that came out of it. Now, some of these were intended to inform government policy, and even during the competition, the Valencia team did some of that work. And now we're working on building on this foundation a more general AI for good ecosystem that could be used in future pandemics, as well as maybe other challenges. Now, one of the interesting outcomes was that we discovered that from those many different entries that had different kind of technology, we could build composites or super predictors and super prescriptors by combining the ideas that were different in them and work differently. And indeed, evolutionary AI plays a role here as well. These blue dots this is the Pareto front of the 2 objectives of the original entries in the competition. And by using this as raw material for evolution can find recombinations of them that perform significantly better across the Pareto front. And this also works better than starting from scratch. So the human insights are useful. We get better performance than we do if we just try to do random explorations as a starting point. So here we can use this evolutionary AI technology to bring the community together, their effort, their insights together, and build something even better. So this is a very interesting suggestion for the future in how the society can deal with these challenges, using AI as a booster and a way of bringing all the insights together. So to conclude, this system is a demonstration of the power of data and machine learning in dealing with challenges like pandemics. We build predictors by using the data, and we are going to forecast the outcomes. And then we build prescriptors using evolutionary AI that can make the recommendations, the optimal policies. Now, this is useful in augmenting decision-making about COVID-19 and probably other pandemics may happen in the future, but also in general in other decision-making tasks. In healthcare, business, education, society, we can get creative and trustworthy decisions because we can evaluate them using the surrogate. So if you're interested, the demo is available on the web as well as the detailed scientific description of it. Thank you for listening.